Today it's a pleasure to welcome Jordi Miralda-Escude for the seminar. So Jordi is a professor at the University of Barcelona in the Institut de Ciències del Cosmos. Is it well
said? University.
So he's been in Barcelona since 2005, but before that he was professor in the US, the Ohio State University, and before that he was at UPenn. So Jordi did his PhD in Princeton, spent some time in Cambridge also, Iowa. He's been doing addressing a lot of topics of cosmology, observational cosmology, in particular gravitational lensing. This is mostly the reason why I happened to meet you during my PhD a few years ago. He worked a lot on the intergalactic medium, reionization, Lyman-Alpha forest, DLAs. I think this is going to be the main topic of his talk today. He's been doing a lot of cluster lensing, large-scale structure lensing. He's interested in many things like Gaia, black holes, new candidates of dark matter, action or wave dark matters, and so on. This is, I think, recent activities. So we will listen to you now. I hope I haven't forgotten anything.
Oh, you've done very well, so thank you very much.
Okay.
Yeah. So thank you very much, Rafael. And I'm really pleased to be back here. I think I remember having given some other talk in this room, this beautiful room. And I'm glad to be here, meet so many friends. I will be happy to discuss with many of you. My talk today will be mainly about DLAs and large-scale correlations we can measure at high redshift through absorption spectra. This is through some work that I did when I was part of BOSS. A lot of other things on this field have been done more recently with eBOSS. I have not been in eBOSS, so I will talk about things that were done with BOSS data. And then recently I'm also interested in other topics, gravitational lensing with these highly magnified stars, also Gaia data, the stellar stream. So any of you who would like to, I'd be interested in talking to any people who are interested in these topics afterwards. Now, let me just start reviewing a little bit the intergalactic medium and the way we observe it through absorption. So you know the Lyman-Alpha forest is seen with more and more absorption at increasing redshift. And this basically absorption by intervening hydrogen in the intergalactic medium is one of the probes that we have to measure large-scale structure. And it's very good at high redshift because whenever we observe the spectrum of one quasar, we get to see this absorption along a whole line of sight. So one can think about this as a kind of mapping of density fluctuations in the hydrogen along the line of sight. It's a one-dimensional map. Then once we get many, many quasars at high redshift, we can get spectra. We can do large-scale structure studies by correlating this. So BOSS was a great thing because of the large numbers of quasars that you could observe. Even though the signal-to-noise and resolution were poor, but the main thing here were the large numbers of quasars and the fact that you could then do correlations across the line of sight and not just along the line of sight. So basically, what we observe, you can think of these quasars as observing the transmitted fraction, the fraction of flux at any pixel that gets transmitted through by not being scattered as a Lyman-Alpha photon when it is at the exact wavelength by neutral hydrogen in the intergalactic medium. This F is transmitted fraction, right? It's e to the minus optical depth, and you calculate it once you have a model of the continuum of the quasar to get the absorbed fraction at each redshift. Of course, each redshift corresponds to, each wavelength here corresponds to a redshift at which the photon can be scattered as a Lyman-Alpha photon. Then this optical depth is just proportional to the density of intergalactic hydrogen. So you have, as in large-scale structure, you know, density is your 1 plus delta. Delta is your typical, your usual relative density fluctuation in large-scale structure studies. You have a neutral fraction here, an average optical depth. That's the Gunn-Peterson optical depth once you have the mean ionized fraction in the intergalactic medium. Then you have another factor, which is basically the factor you get from going from real space to redshift space, right? We observe in redshift space. So then there is this peculiar velocity gradient term that appears because depending on the peculiar velocity gradient, some hydrogen atoms you observe in real space may either get compressed or expanded when you go to redshift space. So essentially this is, you can think of this as observing this neutral hydrogen map that depends on all these things, not just the density, but also the neutral fraction. Then the neutral fraction goes as density, so you get density squared, plus some other term that depends on temperature because of recombination coefficient. This is a detail that, you know, basically not very important here. The important thing is we have this map. Then this thing here means there is a nonlinear dependence on the optical depth. What you observe is really F. And when you don't have very good resolution signal to noise, you know, you cannot really get tau directly. What we observe is just this F. So the point is we have the Lyman-Alpha forest, which is a tool to do large-scale structure at high redshift, and we can cross-correlate many lines of sight by observing this on many quasars. One can simulate this, this thing here basically through doing cosmological simulations of large-scale structure. You get this characteristic cosmic web of filamentary structures, and basically your line of sight goes through this thing. Every time you go through a density peak, you will get a Lyman-Alpha forest line. So many people have done simulations of this. You have your Lyman-Alpha forest absorption lines. They correspond to density peaks when you compare to density in the simulation or temperature, etc. Okay, so what we do in things like BOSS and now EBOSS and many other surveys is that we have, from the Earth, we observe two quasars. Let's say one quasar is here, another quasar is here, separated in the sky by some angular separation, delta theta, and they are at different redshifts. And then along the line of sight, we observe the Lyman-Alpha forest, so we map these spectral pixels to a given redshift. And so we're observing the neutral hydrogen distribution along this line of sight and along this line of sight. And so we can measure correlation of absorption depending on angular separation and redshift difference. The redshift difference, delta Z, is related to some parallel separation. The angular separation, sorry that this is a little bit dark, yeah, related to the perpendicular separation through some cosmological interesting functions, like, you know, the Hubble constant at redshift Z, the angular diameter distance, etc., right? Now, the main interest, I guess the strongest interest in these surveys was that by measuring these correlations, you can get at these cosmologically interesting functions to relate your physical separations to the observed separations in redshift and angle. And then one was going after the baryon acoustic oscillations, which is a feature in the correlation function. You can measure these, so you can do a lot of studies with these. This is, again, the main thing we measure from the Lyman-Alpha forest. As I said, you measure this F, transmitted fraction, at every pixel. There is a mean value of this F, right? And then, as a function of redshift Z, and then you can define a fluctuation, okay? So this is fluctuation variable, just like in any kind of large-scale structure observations. And then you relate this delta F to the underlying mass fluctuations that are represented by some mass density fluctuation delta. Typically, this will be related by a bias factor. So just like for galaxies, when you do galaxy survey, you measure correlation functions along and across line of sight, and then try to relate this delta F to delta. Okay, so the large number of quasars here is the main thing that has allowed for these things. Now, let me just do a summary of large-scale structure studies here. This has, of course, been done for a long time with galaxies, and then in recent years, Lyman-Alpha forest also has been used as a tracer. Usually you define, this is the correlation function in redshift space. You have your large-scale structure variable, in this case delta F. The correlation function is measured as a function of the separation between two pixels, right? And you can put this separation in terms of its parallel and perpendicular components. So as I said, this is related to redshift space separation, angular separation. Then we measure this correlation function not in real space, but in redshift space, right? So in real space, of course, this correlation function is isotropic. Then in redshift space, you get anisotropies. And in linear theory, when you go to large scales, you can very easily understand the origin of these anisotropies and what you will measure. This was all done by Nick Kaiser in 1987. This is a figure from his paper. And then it was all thinking about galaxy surveys. But the nice thing is that decades later, you do Lyman-Alpha forest, and then exactly the same things are valid there. So basically, when you have a Fourier mode with some linear density fluctuation, if you observe this linear density fluctuation across the line of sight, then its amplitude doesn't change. But if you observe it along the line of sight, then the peculiar velocities mean that the amplitude will be increased, right? So in high density regions, things are moving by converging, and then in low density regions, the galaxies or the intergalactic gas is moving away from the voids. So then this increases the amplitude of fluctuations. This zeta is the peculiar velocity gradient I was mentioning you before. In Fourier space, basically it is this is the Fourier mode, parallel component, modulus, okay? And the eta, the peculiar velocity gradient, is related to the mass density fluctuation just through this factor in Fourier mode. So this mu k is the cosine angle of a line of sight of the Fourier mode. This f of omega is this logarithmic derivative of the growth factor. Now, for galaxies, what do we do? If you just take one single Fourier mode, you say the fluctuation in the number of galaxies is equal to the fluctuation in the mass. And there is a bias factor relating the two. Bias factor of the galaxies. It depends on the type of galaxy, so every kind of galaxy may have a different bias factor. But in Fourier space, you have this factor relating the amplitude of the Fourier modes. So then, depending on the direction of the Fourier mode, you have this difference. For the Lyman-Alpha forest, it's exactly the same thing. We measure this delta F related to the mass density fluctuation. We have this bias factor. Now, we have here the second bias factor. Okay, so there's the usual density bias factor. Density fluctuation in mass corresponds to a density fluctuation in galaxies or in intergalactic gas with different amplitude. But here there is the second bias factor, which relates peculiar velocity gradient to what you see in real in redshift space. And so there are two bias factors that are independent because you don't have a linear fluctuation in the case of the Lyman-Alpha forest. Because of that relation, we observe transmitted flux F and its exponential of minus tau, okay? So if you're observing tau directly, tau goes like the number of hydrogen atoms. Number of hydrogen atoms is, of course, conserved when you go from real space to redshift space. You're not making hydrogen atoms disappear or are creating them. You have the same number, okay? So the bias factor would be 1 if you measure tau. But we're not measuring tau, we're measuring F. Then, you don't resolve the lines, you don't measure the regions that are saturated in optical depth, etc. So you have this B eta here, and you cannot just say its value from any analytic model. You have to do, in principle, if you understand well enough the nonlinear evolution of intergalactic medium through this kind of cosmological simulations of the Lyman-Alpha forest, etc., then you can predict it. Okay, but to predict it, of course, you have to know if your simulations, your cosmological simulations of the evolution of the intergalactic medium are good enough, and if you can trust them. It all depends on that. Now, the power spectrum that you can measure from the Lyman-Alpha forest is very simple. In linear theory, it's just the power spectrum of mass fluctuations times the square of this thing relating your Fourier modes in real space to redshift space. So this is the same formula that Nick Kaiser derived in 1987, except that beta isn't just this f of omega, it has this ratio of bias factors here. So in the Lyman-Alpha forest, if you cannot trust, if you do not have simulations you can trust to predict these bias factors, which by the way depend on redshift, you cannot derive f of omega just by measuring this beta, right? You get only the product of this thing. Okay, so I will mention here just what was done with BOSS. In this paper by Bautista et al., the full results of BOSS in DR12 were reported for the autocorrelation of the Lyman-Alpha forest. So this is basically this psi correlation function as a function of perpendicular and parallel separation. This is perpendicular separation here, co-moving megaparsecs. That's parallel separation, co-moving megaparsecs. Okay, this is data. This is best fit model. And again, the main thing that was the goal here was to measure BAO, but you can also measure the whole shape of the power spectrum. So you fit this formula to the observations. In detail, there's many more complications. So I'm not going to discuss here, you know, in more detail the measurements of BAO, because here in Paris you have many people who have worked in detail in this, right? They were the main people who did the work for this Bautista et al. But I will go more to other applications, mainly to DLAs, also mention a few things about the broadband shape of the power spectrum and what we can say about these bias factors I was explaining. So just from the linear part of this, fitting this thing, in principle, we can measure, as I said, two numbers, these bias factors. And here I write these bias factors as this BF, because as I will explain now, this bias factor is the fluctuation in this mean transmitted fraction, F, right? Which is not the same as the bias factors we're used to of galaxies, where we know bias factor of 1 has a meaning, which is that galaxies fluctuate by the same level or the same amplitude as mass, okay? Before we can do that, we have to do a transformation, but this BF is a little bit different because it says how much does the transmitted fraction fluctuate for a given amplitude of fluctuation of the underlying mass fluctuations, okay? So this BF, this bias factor that relates density fluctuations, is a negative number. It can be small, and this is the measured value. And then beta also had a measured value. Now, for the best fit that was obtained from the final results of Bose, the main errors for measuring beta were some systematics that were related to corrections that have to be done on the broadband shape of this correlation function. So you could try to correct for the influence that high column density systems, which is what this HCD means here, are having on the correlations of the Lyman-Alpha forest. And depending on how you deal with these, you got different numbers, okay? So the noise error is quite small, but the systematic error is bigger, and is the main limitation here. So there's systematics arising from continuum fitting and this contamination by damp wings of the high column density systems and metal lines. Ionizing background fluctuations can also contribute, okay? But nevertheless, despite these systematics, we can do a comparison of these numbers to what we expect from cosmological simulations and see if we have some good understanding of this. And we can basically, at least at the basic level, right, do our ideas that Lyman-Alpha forest is arising from an intergalactic medium with a photoionization by a roughly constant ionizing background, do they fit these observations? So in principle, from these simulations, we should be able to predict the bias factors. This is a difference from galaxy surveys. We cannot predict, or at least it is very hard to predict, bias factors of different populations of galaxies, right? Because galaxies are very complicated systems. To try to predict their properties from simulations based on just the first principles. But with Lyman-Alpha forest, this may be not so hard because we can do simulations of the evolution of the intergalactic medium. And so in principle, these numbers are predictable, although of course with also uncertainties from the simulation side and also these systematic errors from the observational side. In more detail, this autocorrelation function of the Lyman-Alpha forest can be shown here. This is also from the paper by Bautista et al. Instead of showing it as before as a function of r parallel and r perpendicular, so you can take wedges. So you can put, you know, basically the modulus of the separation r, and then the angle relative to the line of sight. So you can take this variable mu equals cosine of the angle from the line of sight, okay? So r parallel divided by r. And then you can take wedges. So here, the correlation function is represented as a function of modulus of the separation between 2 points in the Lyman-Alpha forest for different wedges. This one is the closest to the line of sight. Only pairs of pixels very close to the line of sight with this mu larger than 0.95, okay? But I should say something very important here. All the pairs of pixels that have been used to calculate the correlation function are never on the same quasar. You always take pixels on different quasars because otherwise you have some other systematic errors you have to correct differently, okay? So these are all correlation functions measured from Lyman-Alpha forest pixels on different quasars. But now the wedges, we have 4 wedges here. This is the closest to the line of sight, highest mu, and here 0.8 to 0.95, 0.5 to 0.8, and then mu less than 0.5. So this is close to perpendicular, pixel pairs close to perpendicular to the line of sight. And then you can look at the correlation function, so you get these values. Okay, these are the observed points. These peaks here are the baryon acoustic oscillation predicted from the linear theory, and of course this is what one was mainly after. And then these are different models. The curves are different models that are fitted to it. Okay, so one thing that you see is that in this wedge, for very high mu, you see this other feature. And this feature, we understand what it is. It is due to metal line contamination. So that has to be modeled. And so you see some of the systematics that arise, right? Basically, this feature is due to the presence of some lines from silicon 2 that happen to be separated by Lyman-Alpha by nearly 60 megaparsecs, right? So we know, the wavelength of this silicon 2 line. And then when you look very, very close to the line of sight, what happens is that you get your Lyman-Alpha cloud is associated with some metals very close to it, but then because of the difference in wavelength, you get this artificial bump, just the separation corresponding to the lines. Silicon 2, I think, is 1260, and then there's another one on the other side. So silicon 3 also affects the shape here. So all of this needs to be taken into account and corrected, and this was done very carefully by Julián Bautista and others. Then there are other things that you need to introduce to fit the shape. So you see that basically the first line we have is, let's just take the simple formula I was showing before for linear theory, Lyman-Alpha forest, plus some correction for metals. Okay, and then you get the black line. And the black line doesn't fit very well all the points. It provides a roughly okay fit, but there are some clear deviations with the accuracy that you're measuring things here. Right? Then you keep adding more things, like effect from the damped wings, of the fact that you have high column density absorbers. This correction is not just from DLAs, but also your 10 to the 19 absorbers. Normally it's hard to measure their DLA wings, right? Because 10 to the 19 doesn't give you a very strong damped wing. But when you do correlations, of course, this will have some impact on the correlation. So you have to try to correct for that. And there are other effects like these, so UV fluctuations, UV background fluctuations, and then just having a generic broadband to basically account for some other systematics that we don't understand very well. So with this, you can get basically improved fits, right? In the end, you get something that is satisfying, but the systematics of the broadband shape that arise from continuum fitting and this kind of corrections are the limitation here. And maybe this can be, we hope that this can be improved in the future by having better spectral calibration and better models of this contamination by high column density systems, etc. Okay, now what I want to go to is to go a little bit more into these Lyman-Alpha forest bias factors and then see how we can compare to simulation results, and then go to DLAs, where we have measured the bias factor of DLAs. So as I said before, basically, the density fluctuation we measure from transmission fraction is obtained in this way. And we can relate this when you go to linear theory and you think about averaging over some sufficiently large scale to some relative density fluctuation in the gas through bias factor BF delta. And then there's also this peculiar velocity gradient variable. Okay, so both things affect you in redshift space. And here there is a second bias factor. Now, the thing is that these bias factors, when you express them in this way, they are hard to interpret because they depend on the fact that you measure this f equals e to the minus tau. Okay? So you can define these b tau bias factors, which means relative fluctuation in an effective optical depth compared to the underlying mass fluctuations. And these are then easier to interpret, so they are useful to have these bias factors also. The effective optical depth is a concept that has been, defined and used by investigators for very long in the Lyman-Alpha forest. So basically, you think I'm taking my Lyman-Alpha forest lines, they have some distribution of equivalent widths, and then if I integrate, I can calculate the mean optical depth they would contribute, the effective optical depth that the superposition of absorbers would contribute, so that if I have just a bunch of Lyman-Alpha forest lines and they are uncorrelated and they have this distribution of equivalent widths, then on average, the effective optical depth that I will get is given by this formula. My mean absorption F bar will just be e to the minus tau effective, okay? Now this tau effective, I'm thinking about measuring this tau effective over some chunks, over large scales in the Lyman-Alpha forest, will also fluctuate. Will fluctuate depending on these averaged mass density fluctuations on some large scale delta through this bias factor b tau delta, and also on this peculiar velocity gradient factor through the b tau eta. Okay. Now here, it is true that b tau delta of 1 corresponds to what you intuitively think bias 1. So if there is underlying mass fluctuation varies by 10%, okay, your effective optical depth will vary by 10% when the bias is 1. Okay, so bias of Lyman-Alpha forest of 1 would mean this. When you go to this effective optical depth instead of the F, okay, if you have 10% mass fluctuations, then your absorption, effective absorption you measure, tau effective, varies by 10%. If bias factor is 2, then it's 20% when the mass fluctuation is 10%. So that's why it's useful to define this b tau. By expressing this F bar in terms of the average over the whole universe, and then this linear averages over some sufficiently large scales, you can easily understand the relationship between these b taus and your bf's. Okay, there's just this, if you know the mean transmission factors at each redshift, F bar naught, it is just this relationship through a constant. Okay, so then we can re-express these bias factors we measure to these b taus, and then they're easier to interpret and compare to simulations. Okay, this is some example of simulations you can do. This is something that many people have done this, but you can basically try to predict linear power spectrum of Lyman-Alpha forest from cosmological simulations. Okay, and this linear power spectrum, as you know, PF of k, is just the Fourier transform of the correlation function I was showing you earlier that we can observe and compare to this. Now, to understand a little bit what these curves are and the power spectrum of the Lyman-Alpha forest, basically we measure power spectrum of Lyman-Alpha forest also as a function of k parallel and k perpendicular. Okay, and you can express this in terms of modulus of k, and again this wedge, but now this mu is not in real space, it's in Fourier space, so it's mu of k parallel over k. Okay, so now here I'm again taking wedges in Fourier space. What happens is when I go to let me go first to very large scale, so very small k. What do I see here? If I'm taking this PF of the Lyman-Alpha forest and I divide by the linear power spectrum of mass fluctuations, then what I will get is this ratio will go to a constant. And this constant will just be the bias factor squared. Okay? But because it depends on mu, this should be that term bias factor squared times 1 plus beta mu squared. So this is basically the dependence here on mu. For a curve that's close to perpendicular to the line of sight, this is where we are. Then I go parallel to the line of sight, the power is increased, okay, because of the 1 plus beta mu squared. So that's what happens on large scales. Now what happens when I go to small scales or high k? Here the opposite happens. So there is essentially the effect of fingers of God, in the correlation function, right, on the linear regime, correlation function is elongated one way because of Kaiser effect. You go to the nonlinear one, fingers of God, velocity dispersions produce the opposite elongation. So exactly the same thing you see here in the Lyman-Alpha forest. Okay, here on very small scales, there is more power across the line of sight, low mu, than along the line of sight. Along the line of sight, you have thermal broadening, other effects that smooth the fluctuations. Across the line of sight, you have less of that. You have just gene smoothing. So basically, from this kind of simulations, you can try to predict this nonlinear function and then say what are going to be the bias factors. These bias factors depend on all of the nonlinear physics, right? So we can try to predict this and see different simulations. In this case, I'm showing two different simulations with just different amplitudes of the power spectrum, different sigma 8. Okay, and you can see the dependence on various parameters. So this we examined to some extent in this paper with my former student Andrea Borinho y Prats. But what you can get from these kind of calculations and simulations is these predictions, basically. So beta, the redshift space distortion, right, that we have in the power spectrum, as a function of redshift, because we can measure this for several redshifts, okay? Now beta, this quantity, for those of you who have worked on galaxy large-scale surveys, you know beta is your f of omega over b, right? When b is larger than 1, typically this beta tends to be smaller than 1. For the Lyman-Alpha forest, this beta tends to be greater than 1, okay? So you have large redshift space distortions, you know, beta greater than 1. Why is this arising? Because bias for Lyman-Alpha forest, bias factor is small, typically less than 1. Now we can predict these b taus I was talking to you about, okay? This is b tau delta, okay? So this is the bias factor that tells you how much the effective optical depth in the Lyman-Alpha forest is going to fluctuate for a given mass fluctuation. And you see it's less than 1. It's shown here for several models, okay, as a function of redshift, and then these models are essentially varying the amplitude of the power spectrum. There's Planck normalized model here, and then just varying sigma 8, 0.88, then lower 0.76, 0.64. So there's variation so that you know, we can look at the model dependence. There is also this peculiar velocity gradient. It's independent of this one. So there's two bias factors. Of these three quantities, 2 are independent, right? Beta is f of omega times the ratio of bias factors. So here you see that this peculiar velocity gradient bias factor is a little bit less than 1. Okay? If there was not this effect of f equals e2 minus tau, this nonlinearity, this bias factor is 1. This is the thing that is assumed to be 1 in galaxy redshift surveys. Okay? And then you can derive f of omega from your beta. Actually, in galaxy redshift surveys, we believe this b tau eta should not be exactly 1 either. But it should be very, very close to 1, okay? Because there are funny selection effects in galaxy redshift surveys one has to worry about. And maybe if you're interested in f of omega, at some point, you know, this b tau may not be exactly 1. Some people have discussed this about because of selection effects in galaxies. But in Lyman-Alpha forest, this is a more important effect, okay? So essentially, we can make these predictions, and we find that they are so they are approximately consistent with, oh, I had this, sorry, with these measurements, okay. So we have found that these values are, you know, approximately consistent with the observed values within 10 or 20%. But the dominant uncertainties are these systematic errors, okay. So the measured beta, this is consistent with the measured beta, which is between 1.2, 1.6. So there is this high beta factor. This is also, you know, within various uncertainties, okay, that depend on these corrections for the continuum fitting and so on. You know, we can say it's consistent, but not very precisely because there are these systematics. Okay. So one can do also, in addition to the autocorrelation of Lyman-Alpha forest that I've been describing, the nice thing about these studies is that you can do a lot of other studies on cross-correlations. And for every other tracer you find at similar redshifts where this Lyman-Alpha forest is observed, most of the quasars that most of the Lyman-Alpha forest we have is between redshift 2 and 3. So for any other tracer you can do cross-correlations. And an example is with quasars. I will just go quickly through this because I want to go to DLAs. But basically when you have cross-correlation, we can define cross-power spectrum, in this case of f of the Lyman-Alpha forest and quasars. And the linear formula is very similar to what we had before. You have here the mass power spectrum, but now you have the product of 2 bias factors and the product of 2 redshift space distortions, one for the Lyman-Alpha forest, one for the quasars, okay? And again, this is as a function of r perpendicular, r parallel. This is the measured cross-correlation of quasars and Lyman-Alpha forest, in this case from this paper, Dimas-de-Bourboulou et al. That was the final results of BOSS, and this is the best model fit. So, you know, things are consistent in general. The best thing you can measure from these, apart from BAO, which, you know, I will not discuss about this, is basically the bias factor of the quasars. So once you know from the autocorrelation you've measured the Lyman-Alpha forest bias, then from the amplitude of this cross-correlation, you can get the other bias factor, BQ, right? We measured just this product from the amplitude of the cross-correlation. but if we've measured independently the BF delta, we can get the other one. So this gives you a bias factor of quasars, right? Which nicely agrees with the other measurements of the bias factor of quasars we have at this redshift, from the autocorrelation, for example. Okay, so that's essentially a nice confirmation that things are working well. Okay, now let me go to DLAs. I wanted to talk about this in more depth. So you can also do these cross correlations of damped Lyman-Alpha systems with the Lyman-Alpha forest. Okay, and the things that these surveys have allowed is to do large-scale fluctuations. So we can ask, if you have a DLA, and I measure this DLA in a quasar spectrum, then I can look at all the quasars around it, look at the Lyman-Alpha forest, and see how this Lyman-Alpha forest is correlated with the presence of a DLA. So just like with the case of quasars, okay, I think if I look on a parallel line of sight close to the DLA, then on average I'm going to have a positive density fluctuation here, greater density than average. So my Lyman-Alpha forest should have more absorption than average. It's just the usual density fluctuation. There should be a linear theory prediction that works as before. And again, this is, you know, so we can measure this cross correlation as a function of perpendicular and parallel components of the separation. This is shown also here in comoving H-1 megaparsec, and we do the same thing. This was first done in this paper from Rivera et al. 2012, and then we did an update with Ignacy Pérez Raffles, who is now a postdoc at Marseille. And this is showing these counterplots. So this is the best fit model. You see the redshift space distortions here, right? In correlation function, you have more correlation across the line of sight. Along the line of sight, you have the opposite. It is, you know, negative correlation because of the peculiar velocity gradient effect. So this is just Kaiser effect. And this was also in the autocorrelation function of the Lyman-Alpha forest, cross-correlation function with quasars, cross-correlation function with DLAs. So the observations maybe, you know, they also show the presence of this Kaiser effect. Okay, so the nice thing is that from this kind of spectroscopic surveys, you just get the prediction of Nick Kaiser here beautifully, right? Linear theory. You don't need to do anything else from this absorption. The nice thing is that, you know, Lyman-Alpha forest actually behaves quite linearly because Lyman-Alpha forest is more sensitive to what goes on in the intergalactic medium rather than what goes on in the densest halos, right? There's less of fingers of God effects and all this. It's just closer to linear theory, even on relatively small scales, like 10 megaparsecs, 20 megaparsecs. Okay, this basically shows here correlation function at different different R perpendicular wedges. So this is, if I'm taking wedges here in fixed bins of R perpendicular, right, then you see this correlation function. It's negative just because of the definition, right? So, you know, when you're close to a DLA, you have positive density fluctuation, then you get less transmitted flux. Okay, so this definition is, you have more absorption, so less transmitted flux gives you the bias factor. As I said, you know, this BF is negative, then you can go to the B tau, which is what we normally intuitively think of bias factors. So this is basically this correlation function, 4 to 8 megaparsecs, 8 to 16, 16 to 24, 24 to 32. Okay, you detect these things out to quite large scales. One thing that you can do, this is Ignacy, who did most of this work when he was a student at Barcelona, and also he finished some of it when he started his postdoc in Marseille. So this is, you can try to fit for the bias factor of DLAs, because remember now that you have this formula here, right? So again, once you know the Lyman-Alpha forest bias factor, you measure the amplitude of this thing, and this is basically the main thing you get from this fit, the amplitude, and you derive the bias factor of DLAs. Okay, so that's how you derive it from the cross correlation. The measurement of this thing just gives you the product. We've independently measured Lyman-Alpha forest bias factor, so then we derive DLA bias factor. Okay, so then we can say, instead of fitting for the whole thing, let's just fit this thing on rings. Let me just take a ring here within some bin in R, the modulus, okay, and then let me get the amplitude of this best fit to the correlation function, and I will derive this DLA bias factor for different rings in the modulus of separation, and see if this bias factor is constant. Okay, I predict the P of K, right, the power spectrum as a function of K, or the correlation function as a function of R, from my Koldar-Matte theory, which I take to be, the best model for the Planck fit and current constraints, etc. So if this agrees with our standard CDM model, right, I should be getting the same bias factor as a function of distance at every ring. And so these are the best fits, right? And this is a function of R. So this is consistent with getting the same bias factor. Okay, here maybe it starts to be some drop. So you can see that even when you go to rather small co-moving separations, you still don't see nonlinearities effects. Okay. Of course, at some point there should be nonlinear effects, but they're not appearing yet when you do this kind of isotropic fitting. So here we get essentially this best fit, bias factor of DLAs, and also for beta. Sorry, no, this is beta of Lyman-Alpha. As I said, there was some uncertainty on this beta of Lyman-Alpha, so we do this fit to that formula, right? And then you have to put some values for this beta. We take the beta Lyman-Alpha from the autocorrelation measurements, but because there's some uncertainty, we try two different values. And we see that, the bias factor of DLAs we get doesn't depend so sensitively on this systematic uncertainty. There's many other things that we try to vary in the model, see what this DLA bias factor is sensitive to. And essentially, we derive this, we infer this is a quite robust measurement. The bias factor that's average for all the DLAs, right? Because here we just take all the DLAs in BOS, is quite robust, and it's basically 2. This is the same result we got from the previous paper, von Rivera et al. And here we tried to do things better. We looked at several dependencies on things, and in the end we came up with the same number with a little bit reduced error bar. So this basically shows that it agrees well with the CDM prediction. Now, one of the interesting things, so this bias factor is higher than was believed some years ago, based on the fact that essentially, the first simulations of galaxy formation at high redshift were predicting that these DLAs would be arising more often in dwarf galaxies, rather low mass galaxies. And this was then predicting a small bias factor, okay? And also from the absence of many cases of associated galaxies with DLAs when you look around quasars. But so, basically from this cross-correlation at large scales, we find that you need this relatively high, not very high, but relatively high DLA bias factor. So this is good news for 21 centimeter intensity mapping. As you know, some people want to do this kind of observe neutral hydrogen in the 21 centimeter line at redshift 2 or 3. Also to do BAO in the radio, right? You basically just do intensity mapping, collecting the average emission from all DLAs without detecting them individually. And here, the higher the bias factor from these DLAs, the greater the intensity of 21 centimeter emission. So high bias factor is good news for them. Okay, now, just a little bit of interpretation. What do we learn by measuring this bias factor of DLAs? Why is this interesting? Well, essentially what we learn is what is the typical mass of halos that are associated with these DLAs, okay? So we can think of DLAs as basically clouds of neutral hydrogen, somehow associated with galaxies, right? And a long debate that has been going on for a long time is, are these DLAs mostly dwarf galaxies or more massive galaxies or galaxy groups? One thing that became clear many years ago already with the early work of Jacqueline is that DLAs were not accounted for with properties from galaxies that were similar to nearby galaxies, right? You had to have not just the disks we observe around normal galaxies, but more gas, more cross-section. So is this because maybe galaxies have bigger disks, or there are lots of galaxies with big disks, or because there are lots of dwarf galaxies we don't see? Well, at these redshifts, redshift 2 or 3, we have this average bias factor, which it's important that it's only the average one. because there may be DLAs. Of course, DLAs may belong to many different classes of galaxies, some with low bias, some with high bias, and we measure only the average value, okay? But this average value is 2. And we can compare to a simple theoretical prediction, which is what's shown in this plot. So first of all, let's look at this thick line, the one that is at the bottom, right? What is this predicting? So as a function of halo mass, in a simple model here of just calculating the halo mass function according to not just the original Prešekta, but its improvement. I forgot the name now. What is it? The more recent that is used now. Yeah, Thorman, right. Sorry, I forgot the name. So, okay, you predict this mass function, and then let's imagine that all the DLAs were hosted in halos of the same mass. For example, 10 to the 11 solar masses. If all the DLAs were in halos of 10 to the 11 solar masses, then the bias factor would be 1.5. If all the DLAs were in halos of 10 to the 12 solar masses, the bias factor would be 2.5, right? When you go to low halo masses, if all the DLAs were hosted in dwarf galaxies, which are isolated and sitting in a low mass halo, then the bias factor would be close to 1. 10 to the 10 solar masses would be about 1, okay? So in this interpretation, you'd have to say, well, the DLAs are characterized by a halo mass of about 4 or 5 times 10 to the 11, then you get the bias factor you want that we measure, which is 2. Okay. Now, of course, this is too simple, right? DLAs are not all the same, so they will be sitting in a variety of halo masses. In fact, in a very broad range of halo mass. So then you can say, let me assume that halos of mass m, each halo of mass m has on average a cross-section sigma, so an area for observing a DLA if you go through that area, which goes as a power law with mass. So m to the alpha, okay? Here you don't have to assume, by the way, that the DLA is smooth. This sigma just tells you the average area. It could be very clumpy. So on a given halo, it could be that where you see a DLA is just a very fragmented area. The only important thing is the total area, right? So in a halo of mass m, on average, how much area do I have where if I go through this area, I'm going to see a column density above whatever your definition, 2 times 10 to the 20, okay, for a DLA. So I'm going to see a DLA. And it's only the average that's important. So for a halos of mass m, it could be that there's quite a bit of variation, but I want to know the average sigma, okay? So as a function of m. So we just assume that it's a power law, okay? So then early models from simulations were suggesting a power law around alpha of 0.6 or so. Now, if I assume that all halos have this cross-section going as this power law above some minimum mass, and then let me take, for example, minimum mass of 10 to the 9, okay, because we believe that below about 10 to the 9, there's photoionization effects that drive away the gas, there's not going to be any gas, etc. Okay, so all halos above minimum mass of 10 to the 9 are going to have DLAs with a cross-section that goes as m to the alpha. Well then, if alpha is small, let's say 0.5, you know, I need to go to a minimum halo mass that's rather high, 10 to the 11. Okay, so I would have to say that only halos above 10 to the 11 have DLAs. And then with a slope like this, I will get a mean bias factor of 2. But that's, well, it will be rather strange, right, to have such a high minimum mass. I normally think, you know, galaxies and gas should be present already in lower mass scale. So if I want to take a minimum mass of around 10 to the 9, because I'm just arguing there are photoionization effects that drive away the gas, and then there should be gas in all these low mass scales, then I have to have a rather steep relationship of cross-section as a function of mass. So alpha of 1 or 1.1, and then it's okay, right? 1 to 1.1, okay, and then I get my mean bias factor of 2. Or else I have to go to higher minimum mass. Now, the interesting thing is this alpha, just to give you some idea what you expect for this, let's imagine that the area, so the radius that contains H1 to a sufficient column density to produce a DLA is proportional to the virial radius of a halo. Okay? Virial radius, if you remember, goes as m to the 1/3. So the area within the virial radius of a halo goes as m to the 2/3. Okay? So if the DLAs occupy a constant fraction of the virial radius, then you'd have alpha of 2/3. So too shallow if you want to go to a minimum mass 10 to the 9 or 10 to the 10. Okay? If you want to explain your bias factor of 2, you need that cross-section, the cross-section or the region which produces a DLA increases faster than the virial radius, more like m to the 1 or m to the 1.1. This is the same plot, but this is showing, sorry that I didn't put it here. What happens if you say that there's not only a minimum mass, but a maximum mass, 10 to the 13 solar masses? You could say, oh, you know, if the halo is so massive as more than 10 to the 13 solar masses, this is a cluster of galaxies. Okay, the galaxies will have been stripped out of their gas. You will not have any DLAs there. Okay, so it doesn't change all that much. You know, there are very few halos as massive as 10 to the 13 at this redshift. So that's why it doesn't change so that much. Okay, so basically this is the interpretation. Now, more recent simulations that have been done basically show that as long as you put strong winds in galaxies, you will get this effect that the relationship between cross-section and halo mass becomes steep, because strong winds mean that gas is driven away from dwarf galaxies. In massive halos, gas is also, you know, shaken and moved out, but in fountains, most of it may fall back. So then basically the effect is in massive halos, you spread out the gas, get more cross-section for DLAs. In low-mass halos, you remove the gas and you get very few DLAs. And that's a way which you can steepen the cross-section. So I think with recent simulations, this bias factor we've measured agrees, and it is in broad agreement, okay? Now, a few more things before I finish. So you can try to measure this bias factor of DLAs as a function of redshift, as a function of column density. There's no measured dependence. It's quite interesting, there's no dependence on column density. On redshift, we have a narrow redshift range. So yeah, we don't measure a dependence, but of course, you know, once you measure things more accurately over a broader redshift range, I'm sure there will be a dependence, okay? Okay, these different points are different sub-selections of DLAs to check. These we think it was just noise, so okay. But the main thing is basically this is consistent with constant. So basically this suggests, you know, halos of different mass have similar profiles of NH1. Okay, you have the same distribution of column densities in halos of low mass, high mass, so it doesn't depend. Then you get the bias factor doesn't depend on column density. But now you can ask, should this DLA bias factor depend on some other property we can measure? Okay, column density is the easiest thing. We have the column density for each individual DLA. Can we measure other properties for individual DLAs? And then can we see if there is any other dependence? Well, one thing you can measure for DLAs is metal absorption lines. What metals are associated with them? This is rather hard to do for as many as 100,000 quasars in BOS or eBOS, because those spectra are of low resolution, low signal to noise. Okay, you can stack spectra. This is what we did in Mas Rivas et al. You can take all the DLAs, stack the spectra, and see what's the average metal lines associated with DLAs. Okay, so these are some average metal line profiles. Here you got your carbon 4, you know, you double it. You can find many metal lines and get the average equivalent width. We did these things like get, you know, how the equivalent width of metal lines changes with column density of hydrogen. Okay, you can detect that low ionization lines increase in equivalent width as neutral hydrogen goes up, but high ionization lines practically don't. Okay, so this basically confirms some of the ideas about the physics of these metal line systems and so on. But then you can try, you know, if you want to measure if the bias factor of DLAs depends on this metallicity, you have to try to measure this for individual DLAs, not just average. Okay, so that's hard because in a low signal to noise spectrum, you practically cannot detect the metal line. Okay, so then what did we do? So here with Andreu Ariño y Prats, what we did is, let's define a quantity that's metal line strength, which we call S. What we do is we look at the strongest metal lines, and then we basically measure average metal line strength for an individual DLA. Now, signal to noise is very low, so often you do not detect the metal line. But anyway, you can just go to the place of the spectrum where you expect it, and even if it's 1 sigma, you just measure average equivalent width for that. And then you take the strongest metal lines, do an average of them, to try to improve, optimize the signal to noise you get. And you measure this S for each individual DLA. So here is a distribution of S. And we can see how this distribution varies depending on the noise or the errors in each that we calculate for these equivalent width measurements in the DLAs. Okay, so of course the more noisy ones, you just see this thing gets broader. Okay, so then we have this distribution. You should think of this as basically a distribution of equivalent width, average equivalent width for several metal lines. There are some negative ones just because of noise, but you know we get a mean. This is basically the exponential distribution of equivalent width that many people have obtained. Okay, and then now let's look at if there is a correlation of the bias factor with this average metal line strength. So this is what I would expect, that there is a dependence of bias factor on this property, because metal lines, basically if you have more metals, you're probably in a more massive galaxy, right? Mass metallicity relationship. Also, if you have more metals, a given column density of metals will be less saturated if you have higher velocity dispersion. So we also know, you know, velocity dispersion is correlated with halo mass, galaxy mass, metallicity. So both ways, right, we expect that there will be a correlation. And this is what we find. Bias factor of DLAs as a function of this S, average metal strength. There is a correlation, right, as you expect. Strong metal lines, they have higher bias. Low metal lines have lower bias. We did a correction because we know that if the hydrogen column density varies at fixed metallicity and velocity dispersion, you just increase the column density of metals for fixed metallicity. So when we try to correct this S for different H1 column densities, we find that the correlation actually gets stronger as expected. And then we even did some model to account for the large errors that you have for this S for each individual DLA. So these large errors means that there is some scatter, you know. DLAs get scattered in this plot because unfortunately you cannot measure this metal line equivalent width very accurately for individual DLAs. But anyway, this is what we find. There is a correlation. And so what that suggests is that there is a, yeah, well, I'll go to the conclusions, but what that suggests is that this is indeed a physical property we're measuring, this bias factor. It does depend on metallicity, as expected, okay? And that essentially the bias factor of 2 we measure is an average, but that if we get, let's say, the 1/3 of the DLAs which have the highest, the strongest metal lines, the bias factor will be even bigger, 2.5 or even 3 once we correct here for this effect of, you know, random errors scattering the DLAs in these bins in H, right? So these will have high bias factors of 3 or so. Now, once you get to very low metallicity DLAs, weak metal lines, these are indeed associated with the dwarf galaxies, right? These are the ones that are around isolated dwarf galaxies. So essentially, this is something that could be checked at some point, for example, through looking through these associations with galaxies. Much more often, you should see associated galaxies near DLAs for the metal-rich ones. Although this is, of course, hard because, you know, the associated galaxies are often hard to see. Impact parameters are quite big, so one has to look over some sufficiently large angular extent. And often the halos that are associated with DLAs are, you know, groups of galaxies, not just galaxies, or you may have like several there belonging to a halo. Okay, so let me just finish. I'll put here the conclusions. Okay, so I've discussed the Lyman-Alpha forest bias factors. We can measure these Lyman-Alpha forest bias factors. We can compare them to simulations. We have several systematics there, but these can probably be improved in the future in 2 ways. First, better calibration of the quasar spectra to reduce continuum fitting errors, better correction of some systematic effects, for example, due to the high column density systems, better modeling of these, and also, you know, better simulations that will be able to provide better predictions and, for the model dependence and the values of these bias factors of Lyman-Alpha forest. We've measured this DLA bias factor, and this has implications for galaxy formation models. So I think now, you know, people who try to do cosmological simulations at high redshift and study galaxy formation and understand the properties of galaxies should not just compare the results of their simulation to explain galaxy properties today and at high redshift, but should also account for absorption systems, in particular all these properties of DLAs, also metal lines, for which one can make many predictions about this. So the bias factor of this DLA is about 2 on average, is close to 2. Doesn't depend on H1 column density, but strongly depends on the strength of metal lines. So thank you, I will stop here.
Thank you very much, Jordi. Questions?
Thank you, Jordi, for this nice talk. I want to go to your second conclusion, which I didn't understand very well, the effect, the constraints on halo mass. So you said that, and it's written on the slide clearly, that at low halo mass you can blow out the gas from photoionization or from some very strong supernova winds, for example, right? Mm-hmm. And then it just doesn't come into play. And then you said that at higher mass you will get galactic fountains, which will spread the DLA and increase the cross-section faster than you would expect as a function of halo mass. Mm-hmm. But it goes, if you just take supernova, it will go the other way. So supernova are effectively more important at low mass than at high mass. So you will get the opposite effect. So to get the effect that you want, you need another physical mechanism that will blow out the gas into fountains more effectively, more and more effectively as you go to high halo mass. And that is AGN. So AGN, the efficiency, because black hole masses increase faster than the halo mass because of the Merritt and Ferrarese relation, scaling relation, that will give you the solution.
Well, I mean, I haven't thought about differences between supernova-driven winds or AGN-driven winds, but I think, I don't see that this question is so sensitive on this, because my point is basically, if you have these winds, right, so when you go to very low mass halos, you have a starburst, and then the wind will typically be powerful enough to drive away the gas at high speed, perhaps higher than the escape velocity of the halo, or just high enough to really drive it far enough away that then everything is ionized and it'll take a long time to fall back. So most of the time when you look at the dwarf galaxy, there is very little gas there. Basically it's been pushed away by the wind and it's not in a DLA, right? In a more massive halo, the same kind of winds may just produce these fountains. So the gas is blown out, but then a lot of it falls back together with some accreting gas from the intergalactic medium perhaps, right? And then it may be self-shielded a lot more of the time, right? So whenever it's self-shielded, then you get a DLA. Yes. So I think that's basically the mechanism. I mean, I haven't looked in more detail about this, but basically it is true that the simulations have evolved. I mean, people have put different ingredients. So now the recent ones agree much better with this. And basically the key is, if you put winds that are powerful enough, they will produce this higher bias factor on average for DLAs. Yeah.
Okay. Yes, I didn't consider self-shielding. That's essential.
So you didn't say too much about redshift evolution. I mean, have you tried stacking in different redshift bins? You would expect a change in the bias factor, wouldn't you, as you go to higher redshift?
Yeah, the redshift evolution is basically just this result that, that we do not detect any redshift evolution in the bias factor. Initially, so we had some sample here that produced some strange variation, but then when we tried to look at, try to increase the number of DLAs, because we had initially taken a subsample because we were worrying about some systematic errors, but then tried to increase the size of the sample, it just seems to be noise. So there is no sign of a redshift dependence, but of course this is only between redshift 2 and 3.
So theoretically, I mean, you must be going down to somewhat smaller galaxies as you move from redshift 2 to 3 for the peak of star formation, etc.
Yeah, so I would expect that once we go more to redshift 0, then probably the bias factor should be less, because most of the H1 will be seen in lower mass halos, at least compared to the typical ones that are existing there. But so I don't know. I'm not remembering now if there, I think there are other observations, maybe if DLAs at much lower redshift that produce a lower bias factor, right? Yeah, there's someone there.
I was going to ask, are the numbers there, the numbers of DLAs below redshift about 2 is, the number of DLAs at a redshift below about 2 is on the order of hundreds. Do you have the numbers there to be able to evaluate the bias?
Yeah, I think it probably has to be measured in other ways, because in this way, of course, at low redshift, you do not have all these Lyman-Alpha forest lines of sight. But so there are probably other ways to measure this bias factor, but now I'm not sure what the most recent results on that.
Okay, more questions? No? So let's thank Jordi again.